The number 10. Let's look at it. In terms of exponents, if we raise 10 to the 1, your answer is 10. If we have 10 squared, that's 10 times 10, which is 100. If we have 10 cubed, that'd be 10 times 10 times 10, which is 1,000. Are you following a pattern here? What do you notice? How many zeros will 10 to the 4th have when you expand the number? The answer is 4. So when you're working with the number 10, the exponent corresponds with the number of zeros there are. What if we went backwards? What if it was 10 to the 0? Well, according to this pattern, 10 to the 0 would equal 1. Wait a minute. What about 10 to the negative 1? Keep going backwards. Well, we keep dividing by 10, so that would give us 1/10. 1/10 can also be written as 0.1. 10 to the negative 2, we'd have to move that decimal point over again, so it would be 0.01. 10 to the negative 3 would be 0.001, etc. Okay, let's go back. I'm getting ahead of myself. Let's say we have 10 to the 1, which is 10. And we're going to multiply that by 5. Well, 10 times 5 is 50. What about 10 squared times 5? That's 500. What about 10 cubed times 5? That equals 5,000. Do you notice a pattern again? 5 is our leading number, and the exponent tells us if we just had the number 5, how many times we would have to move the decimal point to the right. To get from 5 to 50, you'd move it once. To get from 5 to 500, we would move it twice, etc. What this is giving us, what this is leading us to, is a situation where we can write numbers in scientific notation. What that means is, if I wanted to talk about 3 billion, well, that's a lot of zeros. It takes a while to write. Maybe there's a way. Well, actually, there is a way. We could write this in a simpler way. If we took 3, because that's our leading number, times 10, well, how many times would we have to move the decimal point over? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 times 10 to the 9th has the same value as 3 billion. What if it's 3.2 billion? Well, that number in standard form looks like this. Okay, so instead of just writing 3 times 10 to the 9th, we can write 3.2 times 10 to the 9th. Notice how we didn't write 9 zeros. The 9 is telling us how many times to move the decimal point. This is how you write numbers in scientific notation if they're large. So if I said 4.25 times 10 to the 3rd, what value does this entire number have? Well, I'm going to start with 4.25, And now I'm going to use my exponent to lead me to how many times I move the decimal point to the right. 1, 2, 3. I'm going to put a 0 to hold that place. So 4.25 times 10 to the third is equivalent to 4,250. Another example, 7.003 times 10 to the seventh. Let me start with my given value. And now I'm going to move the decimal place 7 times. 1, 2, 3, 4, 5, 6, 7. And then I'm going to put my commas so that I can be clear on what number. 7.003 times 10 to the seventh, I did my commas wrong, is 70,030,000. Notice when I've been giving these examples, notice that my first number, all right, let's do the markup. The first number, 7.003, is less than 10. Up here, 4.025 is less than 10. 3.2 is less than 10. 3 less than 10. 5 less than 10. When you're going to write a number in scientific notation, the first term is a number that's less than 10, but greater than or equal to 1. So this number is going to be less than 10 and greater than or equal to 1. Writing a number in scientific notation, we will multiply that leading number by a power of 10. So this model is what we can use for any number that's written in scientific notation. (1.25 times 10 to the 1). 3.8 times 10 to the 0. 43.6 times 10 cubed. Let's look at these. This one, we're good. We've got our leading number that's less than 10, greater than or equal to 1. And if we simplified that, we're taking 1.25 times 10 to the 1. That turns into 12.5. That's the equivalent value. We're good. 3.08 times 10 to the 0. The 0 is telling me not to move the decimal place, so I won't. 3.8. We're good. And 3.8 was less than 10, greater than or equal to 1. For this next example, we have a red alert. What? This is not in less than 10. So this number, although it is a number, and we could write what it's equivalent to, so the 3 still tells me to move the decimal place 3 times. However, this leading number was not less than 10. So this is not scientific notation. The number still exists. It still has an equivalent value. It's just not written in scientific notation. So you know what? We can write it in scientific notation. Let's take this number that's equivalent to our imposter, so to speak, and let's rewrite it. 4.36. That's going to make it in scientific notation. But now we're going to have to determine what the exponent is so that it'll move the decimal point to the end place so that the number is equivalent. That would actually be 10 to the fourth. Ah, scientific notation. What about really, really small numbers? What about the width of a piece of paper or the diameter of a human hair? The weight of a dust mite. What if I'm talking about a number that's really, really small? I just made that up. Here we go. Well, here's the value. And my job now is to rewrite that in scientific notation. I know that I'm going to follow my pattern, my first number times 10 raised to an exponent. So this first number is going to be less than 10, greater than or equal to 1. I'm going to focus on these significant numbers here, 6, 3. So to turn 63 into a number less than 10, I'm going to call it 6.3. And now I'm going to count backwards from 6.3 backwards to get to the decimal. How many times did I move that? 1, 2, 3, 4. But I went to the left. So my exponent is going to be negative 4. 6.3 times 10 to the negative 4. That's equivalent to 0.00063. Let's go the other way. Let's start with 5 times 10 to the negative 4. Expand that into standard notation. Well, I'm going to start with 5. I wrote my 5 way over here with space because I noticed the exponent's negative. Negative exponents talk about very small numbers. So we're going to move the decimal point to the left. So from the original decimal point where 5 is, I have to move it to the left 4 times. I'm not going to add 4 zeros. I'm going to move the decimal point 4 times. 1, 2, 3, 4. Wait, there's 3 spots without anything. So that's where our zeros come in to hold the decimal place value. 0.0005. That is equivalent to 5 times 10 to the negative 4.